The discovery announced on October 24, 2025 marked one of the most extraordinary moments in modern astronomy. A moment that pushed the boundaries of our understanding of interstellar objects and opened an entirely new chapter in the study of cosmic bodies that drift into our solar system from the distant reaches of the Milky Way. On that day, scientists using the Meerkat radio telescope in South Africa successfully detected the first ever radio signal emitted by an interstellar comet, designated 3I Atlas. What made this detection so monumental was not only the fact that it had never been done before, but also the wealth of scientific possibilities it suddenly unlocked. For decades, astronomers have been working to understand the chemical nature, physical behavior, and origins of bodies that travel through interstellar space before arriving near the Sun. Yet very few of these visitors have ever been observed in detail. Prior to 2025, only two confirmed interstellar objects, Oumuamua in 2017 and Borisov in 2019, had been studied, and neither of them had produced radio signals detectable from Earth. Therefore, the moment Meerkat detected hydroxyl absorption lines at frequencies of 1,665 GHz and 1,667 GHz, researchers knew they were witnessing something unprecedented. These specific OH lines are typically linked to water breakdown products in comets, and their detection offered direct chemical confirmation that 3I Atlas was releasing material into space, behaving in a manner similar to, but also distinct from comets originating within our own solar system. In the months leading to the October breakthrough, several unsuccessful attempts had been made to observe radio emissions from the comet. Observers in September detected nothing conclusive, highlighting the challenges of capturing faint signals from a rapidly moving object that was still too distant for clear detection. These early failures only amplified excitement once the radio absorption lines finally appeared, proving that while observing interstellar visitors is a difficult task, it is also immensely rewarding. The timing was crucial. As the comet approached the Sun, the increasing heat initiated the sublimation of ancient ices buried deep within its core, releasing hydroxyl radicals into surrounding space. These radicals produced the very signals Meerkat recorded. The telescope then measured integrated fluxes of -7, 9 mJy/km/s and -19, 1 mJy/km/s across the two OH lines, values that astronomers emphasized were not signs of artificial origin or technological interference, but instead perfectly matched natural cometary behavior. Spectral analysis further showed that the velocities corresponded precisely with the comet's hyperbolic trajectory, a path that proved it did not originate within our solar system, but from an entirely different star system altogether. The importance of this detection extends far beyond simply identifying water or volatile materials. It serves as a chemical fingerprint from deep space, allowing scientists to compare 3I Atlas to local comets and uncover meaningful clues about the environments in which planets and stars form around other suns. Reports from Space and Technology highlighted early findings suggesting that 3I Atlas's chemical composition differed in remarkable ways from comets native to our region of the galaxy. Its levels of certain volatile compounds, along with its unique spectral signatures, hinted at the possibility that the environment of its original star system may have been colder, more radiation-rich, or chemically distinct from the environment that shaped our own solar system. Such differences excite astronomers because they provide rare, tangible samples of matter shaped under conditions we have never directly observed. Since its discovery by Chile's Atlas project in July 2025, 3I Atlas had generated great interest among astronomers around the world. Its discovery instantly placed it in the small but growing family of interstellar objects that have wandered near the Sun. From the moment it was identified, researchers noted unusual patterns in its movement, particularly its non-gravitational acceleration, a phenomenon in which the comet's speed is influenced not solely by the Sun's gravity, but also by gas jets erupting from its surface. As sunlight heats its ices, these jets act like miniature thrusters, slightly altering its course in ways that must be measured precisely to plot its true trajectory. This behavior is seen in solar system comets too, but the strength and unpredictability of the jets on 3I Atlas made it stand out as an exceptionally active object. Images captured by the Virtual Telescope project on November 11, 2025 revealed just how dramatically active the comet had become. The photographs showed a long, luminous ion tail stretching across space, glowing with a bluish tint that indicated high emissions of carbon dioxide and hydrogen. This shift in color fascinated observers because it suggested that different layers of the comet's interior, preserved for millions of years in frigid isolation, were being exposed and vaporized for the first time as it warmed near the sun. Analysis of the images suggested that the nucleus of 3I Atlas measured somewhere between 3 and 11 kilometers across, a size considerably larger than the elongated, cigar-shaped Oumuamua, which measured only a fraction of that. Its coma, the cloud of gas and dust surrounding the nucleus, extended up to 0.7 degrees across the sky, making it an impressive sight even through mid-sized telescopes. The comet's speed, measured at roughly 30 kilometers per second, was also far above that of most solar system comets, further confirming its interstellar origin. Comparisons with 2I Borisov, the second interstellar comet, discovered in 2019, showed that 3I Atlas was far more active. Observers reported at least 7 powerful jets erupting from its surface, carving structures into its coma and contributing to changes in brightness that varied from night to night. Scientists attributed this extreme volatility to the countless years 3I Atlas spent drifting through the Milky Way. During that time, cosmic rays continuously bombarded its surface, breaking down molecules, weakening crust layers, and trapping volatile gases beneath them. When the comet finally entered the warmer region near the Sun, these weakened layers fractured easily, unleashing dramatic bursts of gas and dust. The story of 3I Atlas is thought to stretch back millions of years to a distant region of the Milky Way where it originally formed. At some point long ago, gravitational interactions, possibly involving a passing star, a giant planet, or a dense cluster of objects, ejected the comet from its home system and sent it drifting into interstellar space. For ages it traveled alone through cold, dark regions of the galaxy, shaped by radiation and galactic tides, until fate brought it close to our solar system. Its trajectory, identified as hyperbolic, confirmed that it was merely passing through and would not become gravitationally bound to the Sun. After its brief visit, the comet will continue outward and eventually return to the vast emptiness between the stars. During its closest approach to the Sun on October 30, 2025 at a distance of 1. For astronomical units, the comet underwent intensified sublimation. Ultraviolet emissions became stronger, and the ion tail grew even more elongated as solar wind interacted with charged particles escaping from the nucleus. Observers around the world reported fluctuations in the comet's brightness, sometimes increasing noticeably within hours. One particularly captivating sight was the appearance of an anti-tail, an optical phenomenon caused by dust particles, forming a narrow beam of light oriented toward the Sun due to the geometry of the comet's orbit. Anti-tails are rare and visually striking, making 3I Atlas an even more remarkable object to witness. The James Webb Space Telescope added another layer of insight through its infrared observations. These data complemented the radio signals detected by Meerkat, giving scientists a fuller, multi-wavelength understanding of the comet's interior chemistry. Webb's findings confirmed high levels of water loss, further supporting the natural origin of the comet. Together, the combined observations from ground and space telescopes painted a detailed and compelling portrait of 3I Atlas as a naturally formed interstellar visitor, ancient, volatile, and rich with chemical clues that may deepen our understanding of planetary formation across the galaxy.